Okay, I want to give you a little run through. We're going to learn about factoring, and you might be asking, why would I need to be able to factor things like these algebraic expressions? We're going to see them in equations, and that brings me to my point, is that you're going to have equations like you've seen equations in the past, I guess, that have said something like this: 2x plus 1 equals 21, and it's easy enough to solve. We've been doing this for years, since maybe 7th or 8th grade, where you're doing two-step equations, -1 on both sides. So you do opposite operations, you do it to both sides. 2x equals 20, and it's times 2, so you divide by 2, and it comes out to a nice simple x equals 10. Well, that's a basic equation. Here we have what appears to be kind of a basic equation, but it's got a little bit of a twist to it. It's got an x squared in it. Plus 6 and equals -5x. So when I ask students that haven't experienced what we're about to learn, how they solve this, most people say, hey, why don't you subtract that 6 from both sides, and we're left with x squared equals, well, these aren't like terms, so they might say something like -5x minus 6, and then they waffle a little bit at this point. They say, well, maybe I should add 5x to both sides, and they do that, and they get, well, these aren't like terms. X squared plus 5x equals 6, and they get a little stuck. They say, well, divide everything by 5, but that doesn't get rid of the x squared. They say square root both sides, but that becomes a mess. And here's the point, is that it becomes very difficult when you have an x squared and an x term in the same equation to solve it with the traditional method. So we're going to learn something a little bit new, and I thought that was worth just kind of throwing that out there in the first minute or so. We're going to learn how to factor, and factoring is going to help us in the long run solve more complex equations like the one you just saw. In this video, we won't get all the way through, well, how are we going to apply it to solving, but it's the building block for solving more complicated equations. So stick with me. All right, the first thing we're going to do in any factoring problem is we're going to look for what we call a GCF, or the greatest common factor. You knew that as soon as I put GCF out there. We're going to look for the greatest common factor. So something as complex as what I have up here, most people can tell, hey, everything is divisible by 2. In fact, it's got a -2 out there, but I'm just going to address that. Let's get the 2 out of it first. And what we do is we divide every term in here by 2. So this first one comes up to -x to the third. The 16 divided by 2 is 8, and I still have the x squared. The 10 divided by 2 is 5, and I still have the x, and the 80 divided by 2 is 40. So that's a good first step. You're going to see that this looks a lot like this one down here, but I did factor out the negative because with some of my other tools don't like the negative out front. But that's a little bit beside the point at this time, so I'm just going to pull that off there. But the point I wanted to make was get that GCF out first, and then let's start on the rest of this, what I call the factoring decision tree. Okay, and today's focus is on something called a trinomial, something with 3 terms. We're going to use this on probably 70 to 80% of the things that we encounter, the algebraic equations and expressions that we encounter when we need to use factoring to help solve. And so we're going to jump right into this one. In fact, I'm going to expand my screen a little bit. So we've asked the question on this one, is there a GCF? And there's not. So we're going to go right into this new factoring method. All right, or the ability to factor this. And factoring is just breaking something down. If you had a number like 24 and I asked you to factor it, you might say it was 2 times 12, and then you break down 12 into 2 times 6, and 6 into 2 times 3. And at the end, you'd have it factored into all of its prime numbers. Well, that's what we're doing with this, is we're saying what times what gives you x squared plus 6x minus 7. All right, we could do a little guess and check, and if you Google this on the internet, you'll find all kinds of ways of factoring. Some are going to seem a little simpler than the one I'm showing you, but I'm going to show you one that's going to work for all of our trinomials that can be factored, and I think that has some advantages in where we're going. So we're going to label this A, B, C, and you might say, Fisher, you're off a little bit. That A isn't lined up, but the A is actually the coefficient of the x squared term. The 6 is the coefficient of the x term, and the c is the constant at the end. All right, we're going to take those a, b, c values, and we're going to use them in this thing sometimes referred to as the x. In Delta Math, you're going to see what they call the x game, and so on the top, we're going to put the value of a times c. So that 1 that is the a value times the negative 7 is going up here. All right, and the b value, and I refer to those as attic and ceiling. All right, it helps me remember they're both up. All right, there's the attic is above, the ceiling is above, and then b, it stands to reason that we're going to call that the basement. So the b value is going to go down here. All right, so that's our b value. All right, and the question we're going to ask is, what two things multiply to give the top of this x but add to give the bottom? So 7 is a prime, well, it's negative 7, but so it has to be 7 times 1. There's only two things that are going to multiply, whole numbers that are going to multiply to give 7, but one of them's got to be negative. If I make this negative, then they don't add to positive 6. Negative 7 plus 1 is negative 6. So it must be a negative on the other side here, this 1. And when you add these two, 7 and negative 1, you do get 6. So it checks out up above, it checks out below. So now what are we going to do with those? Well, we're going to rewrite our original expression, x squared, but when we get to the b, or the middle term here, we're going to change it. Instead of plus 6x, we're going to use these two numbers we just came out with. We're going to go plus 7x and minus 1x. Do you see how we used the 7 and the negative 1? We split up this b value we're referring to as plus 6x into plus 7x and negative 1x. That seems really strange, but it's fair to do. It's kind of going backwards. We're used to combining like terms. We're uncombining into like terms. All right, so some people refer to this as busting the b's. All right, so we're breaking it up, and then we've got the minus 7 still in the end. So we just rewrote the original expression and we broke up the b values. Now we're going to group this with the associative property of addition. You can think of this as having a plus in the middle right here, and we're going to group the back two terms and the front two terms, and then we're going to factor each one of those individually. So this front set, or binomial, we're looking for a GCF out of that, and somebody might say, I don't see a GCF, there's no common factor with 1 and 7, but there is. It's the variable, and that's the x. So we're factoring out the x. X times x gives you x squared. And then x times 7 gives you 7x. All right. On the other end, I still got plus, and I've got, it looks like a negative 1 is the common factor. And when you divide both terms by negative 1, because that's kind of what we're doing here, negative 1, negative 1. When you divide both terms, you get x, and negative 7 negative 7 divided by negative 1, almost looks like a 7, divided by negative 1 is plus 7. And lo and behold, I want to emphasize that the two leftover binomials are both the same, x plus 7. So it's like a common factor in those terms. We thought we were factoring out to get this, and we were. This x and this negative 1 get regrouped, and then we've got that other common term of x plus 7, and that was a common factor in both of those binomials, and that's our factoring. Okay, x minus 1 and x plus 7. All right, it took me a while to get there. Hopefully you sped up my video, but let's watch that in play on this one. I'll go a little bit faster. A, B, and C, and I'm going to build this x game, so to speak. A times C is negative 18. That was 6 and negative 3 multiplied to give the attic and ceiling, the top, and then the bottom is that negative 7. Now think of two things. Oops, sorry. Got a little problem with my pen there. All right. Two things that multiply to give negative 18 but add to 7. All right. So a little bit weird when it's negative like that, but it's 9 and 2 with the 9 being negative. So negative 9 times 2 is negative 18. Negative 9 plus 2 is negative 7. All right. So I've got the two numbers that I'm going to use as I rewrite the original algebraic expression, that is 6x squared, but I'm going to break up the b term. All right. Instead of writing negative 7x, I'm going to write minus 9x and plus 2x. Now don't those combine for negative 7x? So all we did was break up the b value. Some people refer to it as busting the b's. All right, so that's what we're doing. And then minus 3, don't forget about the c term or the constant. Now I'm going to simply come in here, I'm going to change color real quick, and I'm going to group the first two terms and the last two terms. All right, and I'm going to look for a common factor in each set of binomials. So 6x squared minus 9x, well, there's a common factor of an x, but there's also a common factor of 3. So 3x gets factors out, and I divide each term by 3x. 6x squared divided by 3x is 2x. Negative 9x divided by 3x is minus 3. And then I'm going to go plus, and I'm looking for a common factor here. I don't see one, so that's going to drop back to the default of a 1. And then I'm left with 2x minus 3, the same I started with. But the interesting thing is I got 2x minus 3 as a common factor in both of those sets of binomials. So I'm going to write that one time times the factors that I pulled out of there. So it's kind of like a distributive property in reverse, okay? I think that's the way you'd say that. Yeah, it's almost like a working distributive property backwards. So that's the factoring of it. All right, and you know, I'm going to jump ahead real quick. You can stop if you feel comfortable, you want to give it a try. But take a look at this example, A, B, and C. I'm going to A times C, that's a 1. A times C is 12. The B value is 7. Two things to multiply to give 12. 3 and 4, and they do add to 7, so I'm not going to write the original expression over. M squared, not plus 7m, but plus 3m plus 4m. I busted up the B term, the middle term, and then plus 12. Now I'm going to group these into two binomials being added, and I'm going to factor out, in this case, just the m and m plus 3, and as soon as I factor that out, more than likely the other one is going to factor out to be left with an m plus 3, and it's true. There's a 4 that I divide both terms by, and I'm left with m plus 3. So now I rearrange. I take the m plus 4, put it out here, and the common factor that multiplied by both of those, m plus 3, and that is my factoring of that original term. There are some folks that would show you a step that was not using grouping, but that's going to pay off in the long run for us with some more complicated trinomials, so I hope you'll kind of stick with that. All right, and that's about as much as I want to show, probably more than I want to show in this video. Okay, don't forget to get that GCF out first.